So you've probably seen something like this in math class, an integral like this. Maybe it's, from 0 to 5, and you're integrating f of x. And that's the function that I've got graphed here, y equals f of x in green over here. But what we're going to try to do in this video is understand conceptually what an integral symbol means, and then we're going to try to apply it to some other scenarios. So let's start by trying to understand just conceptually how this integral that you might have seen in math class works. So you might already know that that this integral will give you the area under the curve, right? So it'll end up equaling the area under the curve, whatever value that is, right? So it's going to be all of this area all the way from x equals 0 to x equals 5, right? But let's look at how that's calculated. So f of x equals f of x times dx. Let's just look at this piece right here, and let's forget the integral symbol just for a moment. So f of x times dx, all it is just giving us the area of one rectangle with infinitesimal width, right? In calculus, when we precede something with a lowercase d, we mean that it's infinitesimally small. So this rectangle has an infinitesimal width, which is why we can just say that the height of it, right, f of x here, at whatever x value that is the height of the rectangle. That's why there isn't like two different f of x's, one for each corner or something like that. We can just use one because it's got an infinitesimal width. So now if we look at what the integral symbol is doing, it's just saying, okay, so 1 f of x times dx is the area of one of these rectangles. But now I'm going to add up the area of these rectangles. I'm going to add up all of the f of x's times dx's all the way from x equals 0 to x equals 5, right? So then all it's just doing is, maybe here's the next rectangle, right? The next infinitesimal rectangle. And so we're getting this area right here. And then, another infinitesimal rectangle right next to it, and it just keeps on going. So rather than just writing that this is the area under the curve, what this is really doing, what this integral symbol is doing, is it's saying, okay, we've got f of x at, some x value, x sub 1 times dx plus f of x, and, it's at some other x value. So, x sub 2 dx. Plus, and I'm going to have to do a little wrapping here, so f of x at x sub 3, and I hope that you're getting the idea here is, and it just keeps on going. You're just going to keep on adding up all of these different f of x times dx values all the way from x equals 0 to x equals 5. That's all that the integral symbol is doing. Right? So we're just adding up, all of these different rectangles, all of these different f of x's times dx's, right? Each of these rectangles has a width of dx, and each of them has a height of f of x. And that just keeps on going on and on and on, right? And then from there, we get that it's the area under the curve, right? So all the integral symbol is doing is saying, sum up everything that comes after the integral symbol. And how long are we going to continue summing all these things up? Well, we're going to sum them up from x equals 0 to x equals 5. And that's all an integral symbol means. An integral symbol, right, the s, all it means is the sum, just sum up, right? Sum up the things that come after it. And so that has some important applications. So let's suppose that there was nothing in this integral symbol, right? Let's say that we had another integral that was something like, 0 to 5 dx. And now let's tackle this integral, and let's forget the one up above. So you might say, you could say that, well, f of x is just 1 here, right? And then you draw at 1, I'll try to draw a straight line of sorts. Let's see if I can do it. And then say, and then it's just going to be the area underneath it, right? But so you can pretend that there's a 1 there if you'd like, but we can also just look at it as being just with the dx, the integral of 0 to 5 to dx. And if you do that, you just get 5, the area underneath the curve, of course. But what you're also actually doing, another way that you can interpret this, and is really what you're doing, is you're just summing up all of the dx's from 0 to 5, right? You've got here's one dx, and you're going to sum up all of them from 0 to 5. So all you end up getting is the length here, which is also 5, right? So again, you're just summing up what comes after the integral symbol. So let's do some examples where we get some more visual things. So let's say, and I'll try doing it in a different color. Let's say I had a rod, right, something like this, and we've kind of already done this example up above, right? And the width doesn't matter of it, and I tell you that I've got some infinitesimal, amount, dl, and it's got a total length of L, right? And then I ask you, well, what is the integral of dl? And sometimes you might see it without the limits of integration written. Technically, it would be from 0 to L, in which case that makes the answer more obvious. But the answer here is just going to be that it's L, right? The length is just L. You're just summing up all the dl's from 0 to L. And then, what if you had a sphere? Let's try a sphere. So if you had a sphere, right? A sphere, and it's got some radius r, and maybe that's a dark color. I'll continue using this color. It's got some radius r, so it looks like a circle. It's supposed to be a sphere, and one little piece of it has an infinitesimal area of dA, right? And I ask you, I say, okay, what is the integral of dA for this sphere? And again, you could say, well, it's from 0 to a, but just looking at it conceptually of what the integral symbol means, you're just going to be summing up all of the dAs, the infinitesimal areas of this sphere, which is just going to give you the area of the sphere, which we also know to be as 4 pi r squared, right? And you can also apply this towards charge. So we're going to be dealing with charge a lot. So if you had, say we had like a sphere again. So you had another sphere, and it's got uniform charge density. It's got, charge, maybe it's positive charge all throughout the entire thing, and it's all uniformly distributed. And each piece of the sphere, each infinitesimal piece of the sphere has a charge of dq, right? So dq, where q is the symbol for charge, and then preceding it with a lowercase d just means an infinitesimal amount. So we've got an infinitesimal amount of charge, and I ask you, what is the integral of dq for the sphere? And the answer is just q. We write the total amount of charge as an uppercase q. So uppercase q is just the total amount of charge of the sphere. And again, if you really wanted to be more clear about it, you could write the limits of integration from 0 to q. But conceptually, again, all the integral symbol is doing is just adding up all of the things that come after. It's adding up all of the dq's in this case. And I just want to do one last example here. So let's suppose that you've got a circle. So this time it actually is a circle. It's not a sphere, and it's got a radius of r, right? And I ask you, and then it's got a infinitesimal length here. Maybe I'll draw it just above the circle of ds. And I'm going to ask you, what is the integral of ds for this circle? And ds is, again, just some infinitesimal arc length of the circle. And so you'd look at this, and then you'd say, well, the sum of all of the ds's as we go all the way around the circle is just going to be s, right? Which in this case, s is just, if remembering from like trigonometry and so forth, that if you have some central angle theta, that the arc length subtended by that angle is from, along here to here is S, right? Technically that would be S. And so I'm saying that we're going all the way around the circle. So theta here is going to be 2 pi. It's going to be all the way around. And so you get S. But we also know what the circumference of a circle is, because we're just integrating all of the ds's. So we get the length the whole way around the circle, which is the circumference, which is just 2 pi r, right? So, and in our case, if you really wanted to try to draw it out, we've got some angle here, and I'll try to draw it a little more straight. So we've got some infinitesimal angle here, d theta, and you can probably hardly see that, but it's d theta is this angle, and then ds is the infinitesimal arc length here. So anyway, I hope that this video was helpful in trying to understand integration and getting a more conceptual idea behind it and how to apply it in the problems that we'll be doing.